In the last video, we have started creating core solver part of our algorithm, mainly the output grid class. This video, we will try to finish implementing the core solver algorithm class. Okay, so let's open our core solver class, and another helper class that we will need is core helper, and we will call it core helper. Okay, and we need to create this class. So this class will contain a mix of helper methods used by the core solver class. I admit it could be probably split into multiple classes, but let's implement it as it is. So let's first create some fields. So we will need two float values, total frequency and total frequency log. Those two values will be used with the entropy calculation. And we also need a pattern manager. We'll call it pattern manager. Let's create a constructor. And this constructor will take the pattern manager as input. And we will assign it. And inside this constructor, so we will now loop through each pattern and add to total frequency and then calculate the total frequency log. So let's create a for loop. From 0 to pattern manager, get number of patterns. Okay. And now we will add to total frequency plus equals. And this pattern manager get pattern frequency and pass it I index. And now we can calculate the total frequency log. It will be equal to mathf.log total frequency with base of 2. Now when we create select solution pattern from frequency method, we will take a list of integer called possible values and return an integer. This method is responsible for picking a solution, so collapsing a cell based on frequencies of the possible pattern indices, so possible patterns. We have discussed how it works in theoretical introduction for the collapsing step. We will pick a random value and check in range of which index it falls. So first of all, we need to get the list of frequency fractions for all the possible values, so possible indices. So let's create a new list of floats and call it value frequencies fractions. And we will call get list of weights from indices. And we will pass it possible values. Okay, let's create a placeholder for this method. Next, we will need to create a float random value from range of 0 and value frequency fractions sum. We'll call it random value. And get the value from 0 to value frequency fractions and a sum of it. Here we will need to import link. Okay, next we need a float sum and int index. Okay, now we will loop through each item in value frequency fractions. Let's create a for each loop. And now we will add to sum the item. And if random value is less than sum or equal, we will return the index. So we have found the range where the random value fits, so we can say that this index is the solution. Else, we add to index and loop again. And when we find the index, we return index. And we should add -1 to return a valid index, so the last index in any case. We need to implement our get list of weight frequencies method. Let's change the name to get list of weights from indices. We'll create a list using a link library. So we will call var value frequencies, and we will call possible values dot aggregate. And we will create a new list of floats. So let's finish writing this method and I will explain what it does in a moment. ACC and val will be passed to a lambda expression, and we will create a method here, an anonymous method, and acc.add pattern manager get pattern frequency for val and return as acc. And next we need acc lambda expression acc to list. So aggregate takes an input object, so we create a new list of floats which is represented as acc, so accumulator, and val is the value that we get looping through possible values. Then we perform the acc.add and we add the frequency to our list defined here. And then we always return this list. So each time we pass the same list and add to this list a frequency for each of the indices. And then we return the acc. And because this is a lazy execution context, because it is using aggregate function, we need to call toList to perform this aggregate function and return a list. So if you're not exactly sure what lazy execution context is, this just means that this value frequencies is not performing the calculation until you call on it a method such as toList or a for each loop. Okay, so we now have a value frequencies list of floats and we just return it. Next we will create a method called create for direction neighbors. This will take vector to int cell coordinate, vector to int previous cell, and return a list of vector pairs, another helper class. So let's create a public list of vector pair, create for direction neighbors. As an input, it will take vector to int cell coordinates and vector to int previous cell. Okay, and we will need to create this vector pair class. So let's do it now. Okay, let's add it to our namespace and delete monobehavior inheritance. So fortunately, it's quite a short class. So let's create the fields. We will need a vector to int base cell position property. So let's create it. Prop vector to int called base cell position. Okay, another property called cell to propagate position. Also vector to int. Okay, another one called previous cell position, also vector to int property. And another property called direction from base of type direction. Okay, let's change the name. Now let's create a constructor. It will take a vector to int, so vector to int base cell position, vector to int cell to propagate position, direction from base, and vector to int previous cell position. Okay, and let's assign those to our properties. So when we collapse a cell, we then want to check its neighbors for any changes in their lists of possible indices. So here we will store the cell that has initiated propagation, so the one that has been already processed and now wants to decrease the number of possible indices for its neighbors. We also store previous cell position, so we are looking at all neighbors, but we had to start from somewhere. So we don't want to go backwards when checking neighbors. This is kind of the same idea. If you have played the Snake game on old mobile phones, you could go in three directions but not backwards. So this cell that initiates the propagation is called base cell, cell to propagate is the neighbor that we want to check, and we also store the direction in which we are moving to get the valid neighbors list. So the only method that we need here is to check if we are checking the previous cell again. So if the cell to propagate is equal to previous cell. So it will return a bool value, and it will be called are we checking previous cell again. And we will return if previous cell is equal to cell to propagate. Okay, great. So now we are done with vector pairs. Let's return to core helper to the create 4 direction neighbors. Here we want to create a new list of vector pair. We will call it list, a new vector pair, and we will fill it in with new vector pairs. So here we will create new vector pair for each direction. We will not bother with the fact that there might not be one of those neighbors, so this might be a corner cell and it might not have the neighbor upwards and to the right. It will be checked further in the when the method uses those values. For now we only create 4 vector pairs in each direction, so up, down, left and right. So we create a new vector pair and pass it cell coordinates, cell coordinates plus new vector 2 int for the cell to propagate, and we will add 1 0 to go right, and we will call direction dot right and pass previous cell as previous cell. Okay, let's copy this 3 times. Okay, and now we will need to change those values that we add the new vector to int. For now it will be -1, so left direction, and change the direction. So left. Here we change to 1, so it will be up. And below to -1, so it will be down. Okay, and we will return this list. Now we need an additional method that is called create 4 direction neighbors that gets the vector 2 int cell coordinates. It will be a special case when we pass cell coordinates as the previous cell. So let's implement it. Public list of vector pair, create 4 direction neighbors. So we are overloading this method, and to take only 1 vector 2 int cell coordinates, and we'll return create 4 direction neighbors and pass cell coordinates 2 times. Next we want to create a calculate entropy method that takes vector 2 int position and output grid and returns a float. And this method will calculate the entropy. We first need to create float sum. Next we will loop for each possible index in output grid get possible values for position and pass the position. For each var possible index in output grid get possible values for position. And apparently we have created a private method out of it, so let's go to definition of output grid and get possible values for position was private, so let's make it public. Okay, let's go back, and now we can pass it the position. Okay, so here we will add to the sum the pattern manager.get pattern frequency log 2 and pass in the possible index. So sum plus equals pattern manager get frequency log 2 possible index, and we need to fix the name. And we will return the total frequency log that we have calculated in the constructor of core helper minus sum divided by total frequency. So you might recall it from the calculation of entropy from the slides in the theoretical section. Next, we will want to implement check if neighbors are collapsed. So it will take pair to check vector pair and output grid and return a list of vector pairs. Check if neighbors are collapsed. It will take vector pair to check and output grid. So here we will check for the neighbors that are unsolved yet, and we will return the list of the unsolved neighbors. So let's return, and let's call return 4 direction neighbors, and pair to check dot cell to propagate, and pair to check base cell position, and we will be using the link library. We will call where and x lambda expression output grid dot check if valid position. We will pass x cell to propagate position and output grid to check if a cell is collapsed, and pass it x cell to propagate and equals false. And we will call tool list. So basically we are creating the neighbors and checking which neighbor first exists and second is collapsed. And we are returning to list because it's another lazy execution context example. Okay, and let's finish this class with the last method. The method will be called check cell solutions for collisions. It will take vector to int cell coordinates and output grid and return a bool value. Let's create it. So this method will check if the solution we gave to a cell doesn't cause a collision. So we have collapsed a cell, given it an index as a solution, and we check if neighbor cells has no possible solutions. We have a collision and we need to start over the algorithm. So let's implement it. First we will call for each neighbor in create 4 direction neighbors for our cell coordinates. And here we will call the overridden version of create 4 direction neighbors with 1 parameter. So this basically means we are checking in each direction. Next we will check if the position is valid. So we'll call output grid check if valid position and neighbor cell to propagate position, and if it isn't valid, we'll continue to check next neighbor. If it is valid, we'll create a new hash set of integer values called possible indices. Next we will loop again for each pattern index in our output grid, get possible values for position, and pass in our enable cell to propagate. So basically we'll loop through each possible index at neighbor. And we'll loop through output grid, get possible values for position, and pass it neighbor cell to propagate. We need another brace. Okay. And here we will create a var possible neighbors for base. Here we will create var possible neighbors for base and call pattern manager get possible neighbors for pattern in direction. And we will pass to it pattern index at neighbor. So okay, we need to delete those two brackets, and let's call pattern index at neighbor and neighbor direction from base get opposite direction to. So basically we are taking the possible neighbors in the opposite direction, so from our base towards the neighbor. So basically what is happening here is we are taking all the possible indices for our neighbor, and each of those indices can have concrete neighbors in the direction of our cell that we have propagated. And because we know that, we can check if any of the possibilities can have as a neighbor the value that we have collapsed in our base class. Okay, because this is quite complex, let's see the middle image on the slide. Let's say we have collapsed this cell in the top left corner, and this propagated the neighbors, and we have those two solutions for the neighbors. And let's say we have started from the bottom right cell, and this has influenced the bottom right tile. And it has collapsed this cell to have only, let's say, 0 and 1 as a solution, or 0 as a solution. And then we go back to the top cell, and it might not be compatible with the result of this solution. So let's say we have closed this cell to have 0, and then we check, does this cell upwards from the cell that we have previously collapsed, is it compatible with 0 here? And let's say it isn't. Let's say the 0 can't have the 0 below it, and 4 also can't have 0 below it. So this is the case where there is collision. So setting 0 here from this cell has created a collision between this cell and the cell up from it. And this is the case here. Okay, so let's get back to code. And last step will be possible indices union with. So we are adding all the possible indices in this direction for each possible neighbor in our neighbor cell. So we will union with possible neighbor for base. Okay, so we have gathered all possible neighbor for base cell, and we need to check now if these possible neighbors for base contain what is really in the base cell right now. So if possible indices contains output grid dot get the possible values for position cell coordinates, so the base cell first equals false. So we basically say, can you find the first index that is present in possible indices and also in the possible values for cell coordinates? If there is no such first element, so none of the elements is possible, then we return true. So we have collision. So we have a collision. Okay, and otherwise we return false, so we are good to go. Whew, it was hard, but okay, we are done with the core helper class. Next video we will finish implementing core solver, so see you there.